All right, so today I'm going to be talking to you guys about rare mafic rocks in the eastern Sierra Nevada batholith and what they can tell us or help us understand about the differentiation pathways and possibly the sources of the eastern Sierra Nevada arc. So this is the basic outline of how my presentation here is going to go for you. We of course have our introduction and so on. Introduction is going to consist of the Sierra Nevada introduction, the nature of the mantle, mafic rocks, and what we focus on in this study. You can follow along with the basic outline here up at the top here if you get lost and can't figure out what section we're in, which hopefully does not happen, but just in case. So the Sierra Nevada batholith, most of you are from Southern California or have been here for a little while, and you've probably become familiar with the Sierra Nevada in some capacity or other. But just in case you haven't, the Sierra Nevada batholith is a part of the Cordilleran arc, which is along the western North and South America. It runs from British Columbia up here down through the tip of South America, and the Sierra Nevada batholith falls right about in the middle here throughout California. And so the Sierra Nevada arc was active during the Mesozoic, during the major crustal growth event during the Mesozoic, from about 250 million years ago in the Triassic to about 80 to 85 million years ago in the Cretaceous. It's largely granodioritic in composition, or at least what's exposed now, and it has broad east to west geochemical trends that go from essentially lower silica and potassium contents in the west to higher silica and potassium in the east. Also isotopic trends such as increase in initial strontium values toward the east and decrease in the epsilon neodymium values. Okay. So this is a basic cross-section of the Sierra Nevada arc during the Cretaceous. So we have our magmatism happening over here on the western end. So this is the coastal end of the North American continent at the time, and this is over toward the east. And a proposal for the reason for some of these broad west to east geochemical trends is that there is a juxtaposition of two different types of crust between the two sides of the Sierra Nevada. So in the west, it's proposed that there is the panthalassan oceanic crust and ophiolite sections that are thrust up against the North American continental crust being much thicker and much more silicic. And so the arguments could be you would expect in this thicker crust to incorporate more crustal material, for example, and therefore you would end up with higher silica and potassium contents here, as well as increasing your initial strontium and decreasing your epsilon neodymium. So there are other places that this kind of difference can come from. So it is well established that in the western Sierra, the mantle source is depleted mantle. Many studies have been done, and that's fairly well established, but it has been proposed that some of those differences in geochemistry in the eastern side of the arc, particularly the isotopic trends, could be produced by enriched mantle. So what is enriched mantle? What is the mantle in general? So we can look at the isotopic signatures of different sources of mantle to kind of establish what they are. So depleted mantle is fairly well established. We're fairly well constrained. It has high positive epsilon neodymium values, so that's over here on this chart. By the way, this is epsilon neodymium on the left, initial strontium, also known as 87 strontium over 86 strontium. This initial strontium on the the x-axis. And so here we have our depleted mantle reservoir. And this has, again, a high positive epsilon neodymium between like positive 8 and 10, and fairly low initial strontium values, so 0.703, 0.704-ish. And so enriched mantle is not super well constrained. What they use enriched mantle to explain is anything outside of depleted mantle values, but is still mantle. So these tend to lead into more crustal values. So here's your crustal reservoir here, this big purple rectangle. The crust has generally high initial strontium and much lower epsilon neodymium values. So enriched mantle lies somewhere on its way between depleted and continental crust, or right in this zone of continental crust kind of isotopic values. And again, these are usually lower to negative epsilon neodymium and a little bit higher on the initial strontium. Okay? And so also worth noting is that you can actually mix, so you have, when you create a batholith, you have maybe a depleted mantle source, and you're going to incorporate some amount of crustal material, especially in the more evolved magma compositions. And so you could actually produce this same enriched mantle isotopic values by mixing continental crust and depleted mantle. That could be interesting later on. Okay. So in the Sierra Nevada batholith, I mentioned that they're largely granodioritic composition. There are some mafic rocks. These are our look at the parental magmas of the Sierra magmas. And so Mafic rocks are unfortunately very rare in the Sierra Nevada Arc. They cover about 5% of the exposed rock in the batholith, and they're actually more rare on the eastern side than they are in the west. But a few have been studied in detail. So firstly, we have the Emigrant Gap Zone Pluton up here in the north-central Sierra Nevada. In the western side, we have, for example, Stokes Mountain and the Guadalupe Intrusive Complex. And in the east, we have the Onion Valley Sills and the Summit Gabbro. I'll be focusing on the Summit Gabbro in this presentation. So that's down here in the southeast of the Sierra Nevada. I don't know if you guys in the back can see this little yellow blob is the Kern Plateau. That is where our samples are located, on the Kern Plateau. So again, we're focusing on the Summit Gabbro. There has been some study on the Summit Gabbro, but not much recently. So it was studied in the 1940s and in the 80s, and most of this work was petrography, a little bit of geochemistry, nothing too detailed. Diane's students have been working in this area though for the past few years, finding more bodies and doing a little bit more detailed work on them, and myself included. I am doing that today. So most of what is up on the Kern Plateau, most of these Summit Gabbros are what we call Hornblende Gabbros, and that is what it sounds like. There's a lot of hornblende, there's plagioclase, but these rocks are lacking the early forming primitive minerals such as like olivines and pyroxenes that you would expect to first crystallize out of a primary primitive mafic magma. We can track kind of the primitiveness of these magmas by checking the magnesium number. And so magnesium number is the magnesium, the ions of magnesium divided by iron plus magnesium. So it's kind of the ratio of magnesium to total magnesium iron. And so for a mantle-derived primitive magma, we'd expect the magnesium number to be like 75 to 65. And in these Hornblende Gabbros, they're around 50. So they've definitely gone through some differentiation before this point. But that's what these guys look like right here. We have our hornblende in black, the little white plagioclase layers. Sometimes they're layered, sometimes they're massive. But we have found some olivine-pyroxene bearing cumulates up on the Kern Plateau pretty recently. That's what I did in my undergrad, actually, is first finding these. We went and investigated some more for my master's here. And that's what these guys look like. What we were going around looking for was these kind of little orangish red splotches, and that is the weathering of the olivine. So these are our olivine-pyroxene cumulates right here. Okay, so we want to know now, what can these rare mafic rocks, endemafic rocks, and these exceptionally rare olivine-pyroxene cumulates tell us about the differentiation pathways of these magmas of the Eastern Sierra, and maybe about their source. So I'm going to just briefly touch on methods. You can contact me after this presentation if you're curious about any more of them. I did all of these investigations other than the bulk rock isotopic analyses. So we did, of course, fieldwork and mapping, petrographic analysis, mineral chemistry, mineral separations, and some geochronology. And then bulk rock isotopic analyses were done at UT Austin. Okay. So onward to the results. So field and mapping. My localities, unfortunately, are not beautifully glaciated like they are up in Yosemite. And so they're very heavily forested. They're pretty well covered. So you can kind of see we have these little nubs of outcrop down there. So outcrops are spatially limited, and therefore mapping is limited. And unfortunately, modeling is difficult to do because we have these just small outcrops and you can't see much detail. All right, so here is my map. So essentially this is working off of the base map of Mike Diggles in 1987. That's when most of this mapping was done. And so what we have here is we have Owens Valley over here. Most of you have probably driven through there up at 395 on the east side of the Sierras. And we have these little green units in here. These are the Paleozoic metasediments that the Sierra Nevada batholith intruded up into. There's still a few little bits of them left here and there. The majority of this map is this pink stuff. These are granitoids of some sort. The lighter pink here is undifferentiated. They're mapped as Cretaceous, but really there aren't any dates on them, so they could be Cretaceous, they could be Jurassic, they could be older. These darker pink here, these are the Sacatar granodiorite. These are Jurassic, these have been dated, and so we have some fair amount of that exposed in the Kern Plateau area here. And then we have our purple. These little purple splotches here, here's our biggest purple splotch, but all these little kind of dark purple nubs in here, these are our little bodies of Gabbro that are throughout the Kern Plateau here. And some of them were mapped previously by Diane's students and maybe earlier, and then some of them were mapped by myself. And these bright blue bodies here, these are aplites. So aplites are very fine-grained, very high silica intrusions here, usually shallow intrusions. Okay, and so my bodies are these localities. We have Black Rock Mountain up here in the northern end here, SD, October Ridge, Heliport Ridge, And then we did some mapping over here at Deer Mountain on the east. And so we spent a lot of time looking at this map and all these different outcrops here. And we started noticing that a lot of times these gabbro bodies are associated with the aplites, which is interesting. So they're at least nearby them. They occur in kind of like little areas within those granitoids. And we also have this geochemical anomaly here. So this little stripy area, that is a geochemical anomaly that is a high tungsten molybdenum zone. And that kind of follows in with what we propose to be two potential lineaments of outcrops. So basically we've noticed that all of these aplites and our gabbros sort of all outcrop in these sort of linear patterns here. And there's a lot of roads and such up in here, and so mapping's been fairly well done in here, and so we don't think there's any gabbros up in there. And so it's interesting that we have zones where there are a lot of gabbros and aplites and an absence of them in between. So we propose that these are two lineaments, which basically is just linear groupings of these outcrops here. We have some dates. Oh, sorry. We named these lineaments the Troy lineament because we have Troy Meadows down in this area, and the Highway lineament because Highway Pass is out this way somewhere. And so there have been some geochronologic studies of rocks at either end of these lineaments, and they all come out to about 148 to 149 million years. Okay. And so that age is interesting, and also the fact that these things appear to be in lineaments. That these actually correspond to the accepted age of the Independence Dyke swarm. So the Independence Dyke swarm is a, of course, swarm of dikes. It's 40 kilometers wide and about 500 kilometers long, and it extends from the Central Sierra all the way down to the transverse ranges. And these guys are produced in the late Jurassic, so again, 148 million years ago, during an extension transtension regime when you had some oblique subduction. And so these guys actually generally strike north 30 west, and my lineaments here are about north 20 west, so it's interesting, they're about subparallel to each other. Okay. And so moving on to my actual results from my gabbros here. So we have chemistry on these, of course, and bulk chemistry, here's just a couple of examples of what we see in our plotting. So these gray little dots in here, these are other plutons of the Kern Plateau that are not focused on in my study. What I focus on are these reddish, orangish, brownish ones here. And notice that, so we have nice linear patterns in these gray circles, but then we have divergence in my samples here. So what that supports is the fact that, at least petrographically and in hand sample, you can see that these are accumulated. And so this is what we'd expect from cumulates, is that we have divergence from liquid compositions. And so, for example, in our MgO here, in our magnesium oxide, we have much higher MgO contents in my cumulates than we do in the general rocks of this trend here, and also we have a couple that are a little bit low. And so the reasoning for this is that we have magnesium-rich minerals that are accumulated in these samples, for example, olivine and pyroxene. And in these guys that fall below that line, these are very plagioclase rich. And this is supported by our petrography. We do see that. So we know that these are cumulates, so these aren't liquid compositions. So it's hard to tell exactly how primitive the magmas were that they crystallized from. But what you can use is mineral chemistry. And so, for example, the magnesium number of olivine you can use to establish how primitive this magma was that you've crystallized these minerals from. And so the magnesium numbers of our olivine suggest that these were not crystallized from a primitive mantle-derived magma, or not a primary mantle-derived magma. They're still primitive, but we've lost some differentiation somewhere that we're not seeing. So there's been some stage of differentiation before this point that we're crystallizing now. And so onward to petrography. Again, we knew these were cumulates. We have a range in cumulate textures, so add orthocumulates, if you're not familiar with those names. Add cumulates are the most accumulated, basically. So we have our crystals that are all settled and compacted and in contact with each other, and we've lost a lot of the intercumulus melt. So there's very little of the fluid that used to be between those crystals that's still preserved. Versus orthocumulates are kind of at the other end of that spectrum. There's still accumulation, but we still have a good amount of intercumulus melt. And so the way we can track that is by this hornblende here. So the hornblende here represents that intercumulus melt. This here is an orthocumulant. So you have your crystals that are definitely collected. We've lost some of this intercumulus melt, but they're still kind of floating around. We have a lot of it retained. Okay? And so a lot of our cumulate crystals, we noticed, I noticed, had a lot of resorption textures, we call them. So embayments, dismemberment. Basically, they look like they're being dissolved by the melt they were in contact with. So you can see that down here on the bottom, for example, we have this plagioclase that looks like it has a bite out of it. We have another plagioclase down here that's like totally missing pieces. And so we see a lot of these textures in olivine, in plagioclase, in our both pyroxenes, that these things are clearly reacting with the melt that they're hosted in. And there are also some rocks, not pictured here, that are aphanitic porphyritic at Heliport Ridge specifically, and these indicate that there was crystallization at shallow levels. Oh, and here I want to draw your attention to a plagioclase crystal and an olivine crystal right here. And notice that they are in contact and nothing is happening. That might sound very enigmatic to you right now, but it's going to be important in just a second. So no reaction. In some of my cumulates here, we have olivine and plagioclase that were in contact with each other that are now separated by these corona structures. And so here's our olivine, here's our plagioclase, and these coronas are these kind of zones of several minerals that are kind of encasing the olivine at this point. So what these coronas are, they are pretty predictable in their composition. So we have them in several samples at the SD locality, and they vary in thickness but not in their mineralogy. So what we have is we have olivine here, and it's usually surrounded by a discontinuous rim of ensitite, which is an orthopyroxene, and usually magnetite as well. And then we have a rim of amphibole, usually magnesial hornblende on the outside here. And then we have another rim of amphibole, but it has spinel symplectite in it. So these little worms of spinel that are kind of, in fact, I think you can see them, all this kind of cloudy looking stuff out here. That's because of the little worms of spinel that are in there. Okay? And so these are fairly rare, but they're recorded in literature as a metamorphic reaction. Not always between olivine and plagioclase. There are reactions like this between a lot of different types of minerals. But there are examples of olivine and plagioclase reactions. And what these are is reactions at fairly high pressures and temperatures that have not gone to completion. So that's why we have these different rims here, because they haven't completely reacted. But these are reactions in the subsolidus, so these must have been solid rocks when this happened. And the conditions are usually granulite facies where these happen, so that's fairly high pressure temperature. But interestingly, in our area, there is no evidence for a major post-magmatic metamorphic event. So there's no high pressure temperature metamorphism. All of my rocks still show good igneous textures. The surrounding rocks and granitoids do as well. So how the heck do we have metamorphic textures in one of my gabbros here? Well, there has been some proposal on this that you can form these corona textures essentially as an auto-metamorphic reaction, so not as a secondary metamorphic reaction, if you were to emplace these mafic magmas deep in the crust. And so there's two different mechanisms by which you can do this. My favorite is slow cooling at depth, but there's also been proposals that you can also cause this disequilibrium that induces this reaction by decompressing. But the reaction would kind of go like this here. We need it to be at least at 5 kilobars or higher, which is about 18.5 kilometers deep. So that's big crustal levels or deeper. And so in here, if we emplace here at like 5.5 kilobars, well, this is temperature down here on the x-axis, pressure on the y-axis. So 5.5 kilobars right here. And here's the high temperatures, about 1,000 degrees. And as we cool, we cross these reaction lines where the anorthite, which is a high calcium plagioclase, and your forsterite, which is the high magnesium olivine, they'll react with each other to form orthopyroxene and spinel. And so as you continue cooling at that same pressure, you'll actually have amphibole come in and start replacing the orthopyroxene. And if there's any clinopyroxene, that as well. And so we get those textures by not completing this reaction, but cooling and then moving this so that those reactions are preserved instead of going to completion. So as with any geologic study, you'd like to know how old your rocks are, right? And so we were aiming to separate, unfortunately not zircon from our gabbros, because gabbros don't usually contain zircon. They're silica undersaturated. They're usually zirconium undersaturated. And so you don't expect zircon to form in mafic, especially not primitive magmas. But there is another zirconium oxide that does tend to form in mafic magmas, bedelliite. And so we went ahead and I went to separate bedelliite from my gabbros, and I got no bedelliite, but I did get zircon, which baffled the heck out of me. And so then we have these zircons here, and they're very, very tiny. There's 29 of them. They're very small, about 40 to 100 micrometers in their longest dimension. And so here are magmatic zircons. These are zircons that form in a magma, right? That's not what mine look like. These are nice and elongate, they're well formed, they have their little terminations on the ends. I do not have magmatic zircon in my Gabbro. What I have are detrital zircons. So right in here, these rounded zircons. So you take these guys, you send them through a sedimentary system, you round them, you roll them along. And why do we have detrital zircons in my Gabbro? Well, it looks like they are, we have a lot of resorption textures in some of these. So we have like these little embayments here, these little bites kind of taken out of them, which suggests what you would expect, that they were in disequilibrium with the magma. So the ages, we did some geochronology on them anyway, and the ages we got were from 187 to 187 million years to 2 billion years. We have 3 of those 29 grains that are Mesozoic ages, and those could have come from the earlier Triassic plutons and Jurassic plutons that were in the area. And the rest of those grains are actually, so we put them in an MDS analysis, or Nancy here did, ran these through a multi-dimensional scaling analysis and compared them to different pendants in the areas and north of where my sample site is to see if there were any pendants that kind of correlated with the spectrum that I had in ages. And so it correlated very well. So right down here, FR148, that's my sample, correlated very well with this solid line to harmony A. So if you haven't seen one of these, the dashed lines mean a weak correlation, the solid lines mean a stronger correlation. So I had a fairly strong correlation with harmony A, which is part of the Roberts Mountain allochthon, if you guys are familiar with that. And this is older Northern American passive margin sediment. And so American passive margin sediment, we expect to be in the mid to upper crustal levels above the basement rock in the Sierra Nevada, in the eastern Sierra Nevada. And so this implies that I then may have assimilation of passive margin sediments in my Gabbros, at least at Heliport Ridge. So we also looked at isotopic signatures of these Gabbros across the Kern Plateau here, and they were very consistent. So all my isotopic signatures plot right about here in this little star area. Initial strontium is at 0.7066 in basically every one of the samples, and epsilon neodymium is about -4.1 in most of these guys. They're all within a small range. So these are not values consistent with depleted mantle. So again, here we have our epsilon neodymium on the y-axis, initial strontium on the x-axis, and depleted mantle should be up here in the high positive epsilon neodymium, the low initial strontium. I'm way down here, right on top of the word enriched, right? And so we have, again, a couple of ways we could produce these values. And so we know this isn't depleted mantle, but we know there was some assimilation. And so here's our continental crust. If you mix some depleted mantle with continental crust, you can get these values, or you can get these values from depleted or from enriched mantle. So it's hard to say at this point. But again, there's evidence for assimilation, at least at Heliport Ridge. And because those isotopic values are consistent with the isotopic values of all my other Gabbros, it's possible they all experience the same history and maybe the same amount of assimilation. Okay, and so putting all of these results together, what do they mean? So coronas, they imply that we had an emplacement of our mafic magma in the mid to deep crust. Zircon grains, we mean we must have assimilated some passive margin sediment, at least in one of those samples. Our isotopes suggest enrichment. This could be in the crust, it could be in the mantle. Resorption and recrystallization, so all those embayments and reaction textures that we saw, suggest we had disequilibrium with our magma. One way you can produce this disequilibrium is by decompression. So perhaps we had these guys being decompressed along with the coronas from that mid-crustal chamber. We'll get into that in a minute. Fine grain textures imply that we had crystallization in the shallow crust. We had some cumulate textures, differing degrees of cumulate textures in these crystals that have been resorbed and recrystallized. And so these different degrees of accumulation might mean that we have different mechanisms of emplacement. And we've crystallized in the shallow crust at about 149 to 148 million years, same time as the Independence Dykes swarm. So this emplacement event may be related to the Independence Dykes swarm. So back to that little star that I had at the bottom of our Cordillera here, the Torres del Pi intrusive complex down in Patagonia. And so we noticed, and I'll get into detail on these, but we noticed that there were several features of the mafic portion of the Torres del Pi that we had in common with our Kern Plateau Gabbros. And so they have an upper Hornblende Gabbro that is similar to the Heliport Ridge and our October Ridge Gabbros. Their lower Hornblende Gabbro is most similar to Deer Mountain, and they have a feeder zone that is very similar to the SD Gabbro and to Black Rock Mountain. So a little bit of background on the Torres del Pi. It is Miocene, it's 12.5 million years old. It's well glaciated, so this is a laccolith sill complex, and they've basically glaciated down so that you can see a vertical section through this, and so you can see the entire sequence pretty well. Leuthold et al., who studied the Torres del Pi, they propose a deeper source. We'll get into that in a second, but here we go. Here's an outcrop of what these look like. So we have our lower Hornblende Gabbro down here. We have monzodiorite sills, so we had a little bit of bimodal character to this. We have our upper Hornblende Gabbro, and we have this granite that they were intruded into. Okay, and so this is their schematic for how this worked out. And so you have your feeder zone over here, and then you have your sills that are these little dark zones in here. And so they propose, and I'll show you this on the next slide, but they propose that you had a deeper mid-crustal magma chamber, which had components that were remobilized and kind of stuck in that feeder zone. So here you go, here's their model. So we have our mid-crustal chamber here, and we have these little areas that are still fairly liquidy, the rest is fairly crystallized. And then they have remobilized, and the feeder zone has remobilized crystals that you can see disequilibrium textures in, similar to what I have. And then you have your sill complex where those derivative melts have injected. And this is a little bit more of a zoom in on the lower Hornblende Gabbro and the upper Hornblende Gabbro, their schematic here, where we have multiple injections and layers. Down here in the lower Hornblende Gabbro, what distinguishes this is that there are more early primitive minerals in the lower Hornblende Gabbro than there are in the upper Hornblende Gabbro. These are more liquid compositions and a little bit more evolved. But these little kind of stippled areas in here show you areas of greater accumulation. So it is variable across their sills. You have pockets of much more accumulation. You have pockets of derivative melts that are being separated, and they're more fluid rich, they're more evolved. And so it is a little bit compositionally variable throughout here. So our feeder zone here, firstly, this is the Black Rock Mountain dike. It is a vertical dike, and it had a felsic pod within it that we were able to date. We got about 148 million years off of that. And so at SD and at Black Rock Mountain, we note much more extreme accumulation than at other sites that we have. And so the way that we mark extreme accumulation is a greater loss of intercumulus liquid. And so for the most part, we can track that with our hornblende here. So here's the green, that's our hornblende. And so you'll notice that a lot of these larger crystals in here are in contact with each other. There's also a lot of embayments and such, but they're all in contact with each other, and there's not that much intercumulus liquid left. At the Black Rock vertical dike, by the way, it's almost monomineralic. That's important to note, that when you only have one mineral in there, that's not normal for a liquid to crystallize only one mineral. And so that means that we had pretty extreme accumulation to collect all of those together. And also the extreme chromium content suggest extreme accumulation as well. So there's evidence for a deep source, at least at SD, where we have those coronas that are formed between olivine and plagioclase, which suggests that we had solid rock in a deep crust, or a mid-crustal chamber at least, that was then moved. And we propose these were moved as otolith. So essentially, these are solid rocks that were part of the chamber that were then remobilized, but they remained solid, so they weren't disaggregated. And then those olivine and plagioclase in the rocks that are in contact, but they aren't forming coronas. Those, we suggest, are separate crystals that were part of the crystal mush before they were remobilized. And so they didn't sit there in the subsolidus and react with each other. Okay. And then we have some possible crystallization from segregated melts like you see at Torres del Pi. So, for example, down in here, we have Cumulate. This is an anorthosite, so it's almost entirely plagioclase. And whenever you see, again, almost monomineralic rocks, there's been some extreme accumulation to collect only one particular type of mineral together here. And these we think could be from the segregated melts, because there's also hornblende in these as well. And so the hornblende plagioclase is a more evolved composition than those Olivine-Pyroxene cumulates, but these are very close by. They're associated with each other pretty closely. And so also you can check the mineral composition. So in these plagioclase of the adcumulate of the anorthosite, the calcium contents of these plagioclase are significantly lower than they are in the cumulates that are the Olivine-Pyroxene cumulates. And so in these guys we have like a composition of like anorthite 90 to 100, versus in these anorthites we have a composition of more like 60 to 70 anorthite. Okay. Oh, and here's a good example of that resorption that we were talking about, these crystal liquid reactions. So here's our hornblende out here in the brown, Here's a plagioclase crystal and this big old bite taken out of it. We had a little olivine float into the hole there at some point. So these guys have definitely reacted with their liquid and then reaccumulated. Okay, so the lower Hornblende Gabbro is most similar to Deer Mountain. And at Deer Mountain, they are subhorizontal. This is a full complex of subhorizontal layering of cumulates, and so it suggests this is a sill complex. And the layers are the most primitive mineralogies at the bottom. So we have a lot more olivine and pyroxene at the bottom, and it grades upward into more evolved mineralogies toward the top, something they also saw at Torres del Pi. And there's a lot more hornblende, and there's no more olivine at the top, and very little pyroxene. So the layers are also, this is another feature that was seen at Torres del Pi. The layers are interrupted by braids of more evolved liquids. So you can cause this by either re-injecting with another felsic or more felsic magma, or you can filter press, so you can have your cumulates be pressed, and then those derivative melts in between the crystals are kind of shoved up through the rest of the stuff. So you can kind of see that here. Here's an olivine pyroxene cumulate, and these little kind of squirts of coarse-grained stuff in here, they're almost entirely plagioclase hornblende, and these are the more derivative melt that have kind of interrupted those layers. And there's a lot more clinopyroxene here. That could mean that we're seeing a more primitive side of the sill, or it could mean that we may have a drier magma in this region. All right, and the upper Hornblende Gabbro here is very similar to a heliport and October ridges. So this is heliport ridge here, that's me for scale. And so these are subhorizontal. They're fairly tilted, but they're not vertical by any means. And so these are also appearing to be a sill complex. And so we have our olivine norite, which is just olivine or orthopyroxene cumulate with some plagioclase and lesser hornblende. So the mineralogy is very similar to what we see at the SD body, but the accumulation is less intense. So we have, here's our green throughout here, that's our hornblende, our intercumulus liquid. And there's a lot more of it at this site. We still have a lot of cumulus crystals that are clearly in reaction with the melt, but they're not as shoved up against each other, they're not as collected as they were at SD. And so some of these crystals are clearly what we consider to be inherited, which we're talking about. They've had their crazy long past of being crystallized in that mid to deep crustal chamber there, and they've been moved up and they've been reacting with the melt from decompression, and it's just been a horrible ride for them. So here's our big plagioclase right here, for example. And notice we have this big old channel carved into it. It's very unhappy. But we have a whole bunch of small plagioclase very nearby that look fairly happy. They're euhedral, and so it appears that these have formed later on. So we had this earlier formed crystal that reacted with the melt. This was the inherited crystal, and then we had new plagioclase crystallize out of that intercumulus melt afterward. Okay, and so we have some associated rocks with this basal cumulate that I showed you, the one that has the olivine and the pyroxene in it. And they're more evolved, and they are much finer grained. And so we have a variation in texture, but we have some of our hypabyssal textures very close by this cumulate here. And so we have like still some inherited crystals, so still some very unhappy old crystals here. So these are plagioclase. They're all cloudy. They have holes in them. So these have come from an earlier stage, but then you have new plagioclase that's crystallizing on the outside of them, this clear, beautiful, smaller plagioclase out here. And then we have these little hornblendes in the background. And October Ridge, we don't have as much field stuff to look at there, so it's not as clear that this is a sill complex at October Ridge, but it is layered. And we have more evolved mineralogies there as well that are very similar to what we see at Heliport Ridge. So we have basically one big difference when we say more evolved mineralogies. They're still mafic, but we have less anorthitic plagioclase. We have green hornblende instead of brown hornblende, which was mentioned by Luthold et al., that they think is a more evolved version of the hornblende. And we also see a lot more primary biotite and some apatite in there as well. So we see both of those features at Heliport Ridge upper sequences and then the October Ridge. Okay. And so here's a little breakdown of these comparisons that we've made. So we have the feeder zone down here, and we see strong accumulation of the main points, evidence for deep sourcing both in the coronas and maybe in those reacting crystals that look like they have been decompressed, remobilized. And then we have that vertically oriented dike that is clearly extremely accumulated. Lower Hornblende Gabbro, we have Deer Mountain, which is clearly a sill complex, and it's more primitive at the bottom than it is at the top. And at the upper Hornblende Gabbro for Heliport Ridge and October Ridge, We have more primitive mineralogies at the bottom again, and we have more evolved mineralogies in association, and they're more liquid-like compositions, which is like what we see at Torres del Pi. Okay, so now with these observations that we've made in our results and the comparison to the Torres del Pi, we can postulate a comprehensive model. And so for the middle crust and the very far upper crust of the eastern Sierra Nevada, which hasn't really been proposed before. So even though these outcrops are isolated from each other, we see a lot of features that each one has in common with one of the others. And so we can say that they've either had, and the isotopes suggest they had similar sourcing at least. And so we combine them together for this model in the assumption that they're either part of the same system or very similar systems. And so we're going to take a look at a cross-section through these two lineaments. And so here's our proposed model here. It's a little schematic. This is very compressed, of course. Lower crust to upper crust would take up a lot more space. These chambers would not be nearly so close to their sill complexes, but bear with us on the compression there. And so what we're looking at here is we have in the upper crust, we have our sill complexes that were produced by your 150 million year old extension, that extension trends tension event that produced the Independence Dykes swarm. So we had these mid-crustal chambers here that were starting to crystallize, maybe more so over here in the western lineament, the Troy lineament, versus the eastern one here. But we can only say that based on the fact that we see some remobilized crystals here and not on this side. And so while these chambers are sitting down here in the mid-crust, we had that extension event. We tapped these chambers perhaps and taken some melt and some crystals with us and move them up to these sill complexes that were allowed to go shallow because of that extension, right? And over here on the Troy lineament, we have our coronas. And so those coronas, we must have formed in the subsolidus at deep levels, right? And so here we have our crystallization of those olivine and plagioclase. And those were broken apart and brought up as solid rock, right? Versus the crystal mush that had those disaggregated crystals that were moving up as well. And so in those disaggregated crystals from the mush, they would have reacted with their surrounding melt, either by a change in temperature or from just a decompression reaction, so that they were no longer in equilibrium when you decompress them. And so we know that these guys have experienced some assimilation, at least in the west, at the heliport ridge. We had some assimilation of passive margin at mid-crustal levels. And so that may have happened over here as well. We may have some assimilation of those same passive margin materials. We know there's enrichment of some sort that has happened. We don't know if the enrichment is down here in the mantle, and we've had enriched mantle. Could also have happened here in the deep crust, so where our magmas are coming out of the mantle, they could have stalled in the deep crust and mash zone and assimilated some deep crustal material. Or it could have happened all here at mid-crustal levels. All we know is there's enrichment somewhere, and it could have come from any of these places. Okay? And so, to conclude, we have magma from a partially crystallized magma chamber in the middle crust, and it has remobilized to shallow crustal levels and taken solid autoliths and crystals with it. And this likely happened during the extension event that produced the Independence Dykes swarm. That would have given us our mechanism to get these to shallow levels as well. The isolated outcrops may represent two magma sill complexes, sorry. They may be part of a dual sill complex, forgive me, and one of them preserves a feeder zone. And the parental magmas are enriched. We just don't know if they were enriched in the mantle, in the deep crust, or in the, it could have entirely happened at those mid-crustal levels with that passive margin sediment. Okay, so some work is being performed on these two lineaments out here, these proposed lineaments that we have. So those aplites that we mentioned in our two lineaments that seem to be associated with our gabbros, they haven't been dated, so they'll be dating them here the next spring and summer. So if we can show that those are Jurassic, that will support our idea of, firstly, these intrusions being bimodal, and secondly, that these are, this is an Independence Dyke related event. And also epsilon hafnium will be analyzed for those zircon grains as well to help support the provenance. And delta 018 of Olivine-Pyroxene will be performed, and it will give us a little bit more information about that, that parent magma to these rocks that we've seen. So I want to thank many people to thank here. Thank you to Diane Clemens, not my advisor, who is goofing with her former student Michelle here, and the Gabbro girls. Thank you to Phil and Valley for their support on my thesis. So Phil here, and Valley down there grading with me on the field camp. Thank you to Nancy for much help in the field and in the lab, much help in the lab. Dustin constantly helping me in the lab by accident. I don't think it was always his idea, but I was able to drag him along with me many times. I appreciate that. To my husband for drilling things for me sometimes. That's always nice. And so here's your pet rock out in the Dam Black Hall, out in the loading dock there. If you guys have seen the big boulder, there it is. That's my boulder. So these firemen came by to watch us drill because, of course, we're drilling in national forest, and that scared them a little. And they found this rock and were like, "Hey, let's clean it up for you and take it home." So that's why we have this lovely pet rock in the loading dock now. And I'd also like very much to thank the mountain lion for not eating us at Deer Mountain. And that's why I'm Kitty Chow. Thanks, guys.